So now we just saw a lot of formulas with a mixture of quantifiers and different meanings. But suppose somebody gives you a formula like that. How would you go about figuring out whether it's true or whether it's false? How would you evaluate this formula? We know how to evaluate propositional formula, and or of two things is true if at least one of them is true, and so on. But how would we evaluate a formula with quantifiers, let alone with a mixture of quantifiers? So, suppose somebody gives you a formula without free variables, or sets the free variables to some values, and now you want to figure out whether this formula is true or false. In order to find out, we'll play a game. And the game will have two players. One of them will be rooting for the formula being false, and another one will be rooting for the formula being true. The one who wants it false will play on universal quantifiers and will try to mess up the formula by suggesting the settings for those variables under universal quantifiers that are counterexamples. Then the existential player, the green one, whenever she gets her turn to play on the existential quantifier, she will try to find a value of that variable that's a witness for which the formula will be true. So now, whether the formula is true or false depends who has a sure way to win. Since the formula is always either true or false, then at least one of them has a way to win no matter what the other player is doing. So again, we'll have two players. The player holding the existential quantifier plays on existential quantifier turns and tries to find the witness and show that the formula is true. And universal player suggests counterexamples. He really wants to make the formula false. Let's try an example. So here is a formula. For every x, there exists a y such that for every z, x is not equal to y times z. Wait a moment, that's a mouthful. Let's try to understand what the formula is saying first. So let's see, no matter what integer x we pick, there will be some integer y that depends on that x, such that no matter what the other integer z you get, x is not equal to y times z. You may be thinking, well, let's see, if x is something like 2 and y is something like 3, there is not much you could multiply by to get an x, but this should work for every x. How are we going to do it? Let's try to play the game. So we have three quantifiers. The first one is universal, second one is existential, and the third one is universal again. So our universal player, the one who wants the formula false, will go first. Then the existential player will respond. And then the universal player will set the last variable z to whatever he wants. Let's try it. The universal player says, well, I need to set a variable x to something that will mess things up for the existential player. Let's set x equal to 0 and see if she could do anything about that. Okay, can she? What can she reply? Well, maybe she will want to set y, her existential variable, to 1. Okay, is it going to work? It will work for a lot of different z's, but is it going to work for every one of them? Here is where the universal player gets his turn. Again, it says, aha, now I could set z to be 0 as well. And no matter what your y was, if my x is a 0 and my z is a 0, then x should be equal to y times z. There was no way for her to win this game, because the moment he said x is equal to 0, well, there really not much he could do. And this is because the formula is false. Even though when you look at it, it's not entirely obvious that it's false. It's only false because you could set x to be 0. So if it's only false because we could set x to be 0, what would happen if we don't allow the universal player to set x being equal to 0? For example, let's change the domain of x. Let's say that x can only take values 1, 2, and 3. Now, what is he going to do? Let's try. Let's see what he would play. So now, the first step, he has a choice of playing either 1 or 2 or 3, setting x to be 1 or 2 or 3. Let's say he sets it to 2. What is she going to do? Well, how about setting y to be equal to 3? Remember, we are over integers. Is there any way that he can now find a z such that z times y is equal to x, where z has to be an integer? Let's say he tries 0, but 2 is not equal to 0 times 3. He may try 1, whatever. No matter what he tries, 2 is not equal to another integer times 3, just because 2 is not divisible by 3. So in this case, she wins. Notice that she needed to make a right choice in order to win. If she would take y to be equal to 1, she would lose, but she had an option of making the right choice. How did she decide what to take? Well, for example, maybe she looked at the x that he picked and said, why don't I take the same number plus 1? Then it's guaranteed that it's not going to be divisible. Notice that here that she cannot quite pick y beforehand. Well, in this particular example, maybe she can, but in general, she really needs to know x before she makes her choice for y. And this is why we are going in that order of quantifiers. The very first quantifier variable x can be set without knowing anything. The choice of second variable y depends on what x was. The choice of z depends on what x and y were. Every next variable, the choice for it will depend on the values of the previous ones. And here is another example, just like in Everybody Loves Somebody, where the choice of quantifiers really matters. Okay, so now let's try a slightly more complicated formula. So far, we mainly dealt with formulas where we just had one predicate and nothing else. Here, we also try to take our original formula for all x there exists y such that for all z, x not equal to y times z. But now we want to correct it without changing the domains. We could say, oh, wait a moment, either x is equal to 0 or what I expected to be true is true. Either x is equal to 0 or there is some y such that for every z, x is not equal to y times z. Now, is this a fix? Is it going to be true? So again, the order of quantifier didn't change, so our universal player, the red player, is going to go first. Can he again play x equals 0? Well, if he plays x equals 0, then he lost right away. They don't even need to continue, because the formula really is an or of two things, x equals 0 or that other part about exist y for all z, x not equal to yz. If x is equal to 0, the formula is already true. They don't need to bother playing the rest of the game. But he doesn't want the formula to be true, so he better select something other than 0. Let's say he takes 2. What is she going to say? Say she will use the same strategy as before and take the x, add 1 to it, and reply with z. Maybe let's y equal to 3. Let's see if he's going to be able to beat z. Z equals 0 doesn't work. he gives up. So you see, in this case, she had a strategy to win no matter what he picks, because in this particular situation, picking a 0 would result in him losing right away, so he couldn't pick the 0. And 0 was the value for x that allowed him to win the previous time. Okay, so let's try another formula with different order of quantifiers and see if this formula is true or false. So first of all, if you have several quantifiers of the same type, one after another, then the same player keeps selecting values. So this time, the universal player selects both the value for x and the value of y, and the existential player only gets to select the value for z. So let's play it. The first two turns will be the red player, and the last turn will be the green player. Say he selects x to be 2, and then he selects y to be 3. So far, so good. What is she going to say to that? So far, x is not equal to y. Can she find a z that would make the two products equal? And indeed she can. She said, well, take z is equal to 0. No matter what your x was, no matter what your y was, z equal to 0 is going to work, because both x times z will be a 0 and y times z will be a 0. So she wins.